Here we are, back with a new chapter, new topic. I feel like chapter 4, this one will be kind of weird, but not too complicated, I think. Not too much calculator-heavy stuff, if that makes you happy. Yeah, just more thinking and, yeah, not too bad. So I hope that makes you feel better and less nervous about it. Anyway, this chapter is number theory, which it can get complicated if you're I don't know if you take a lot of math classes. Number theory can get complicated, but we're not going to get too complicated. Number theory is just studying numbers, and then the first section we're going to focus on prime numbers. So just to refresh, I'm sure you've heard of a prime number. If not, that's fine because we're going to define it here in the first part of this section. A prime number is an integer greater than 1 that is not divisible by any other integer. Integers are basically whole numbers and integers are the same thing. I would just think of an integer as, well, they said greater than 1. So an integer greater than 1, that means 2, 3, just the counting numbers, I guess. So no fractions, no decimals. We're just looking at the positive counting numbers and not 1. We don't talk about 1 as far as prime numbers go. 7, 8, on and on forever. So anyway, just to get that out of the way, don't worry about memorizing what an integer is. Just, I guess, know that when we talk about prime numbers, we're only looking at positive whole numbers, not negatives, not fractions, no decimals. We don't even discuss what prime means for those. It only makes sense in the world of these whole numbers that are greater than 1. But anyway, a prime number is an integer greater than 1 that is not divisible by any other integer aside from 1 and the number itself. So for example, 7 is a prime number because no other numbers lower than 7 divide into it evenly except 1 in itself. But 6 is not. Oh, look at that. And the reasoning for that is because, this is too distracting, I think. 2 and 3 divide into 6. So it's not just the number 1 in itself. 1 and 6 divide into it, but there's another option. That's why it's not prime. But 7 is because there is no other number besides 1 and 7 itself that divides in evenly to 7. Okay, that's good to know. All right. What we're going to discuss in this section, for the most part, is prime factorization of an integer. The definition of it is the prime factorization of an integer greater than 1 is an expression of the integer as the product of prime numbers. So even just a very simple one, for example, the one that we were looking at here, 6, his prime factorization is 2 multiplied by 3. And that's it. So basically you break it down, think, for example, 6, okay, what two numbers can multiply to make 6? Okay, I would think 2 and 3. And then I would check those, are either of those not prime? 2 is prime because nothing divides into 2 other than 1 and 2 itself. Same thing with 3, so we're done. But if they were more complicated, like we'll see coming up in this section, if I break the number down into 2 parts, something multiplied by something, and one of those or both of those somethings are not prime, I'd have to go further and break it down. So kind of breaking a number down to its building blocks, I guess. That's what I think of it as, and it kind of helps me that primes are the building blocks of all integers. Every integer is made up of primes. Building blocks of integers. I don't know if you're into Legos or you have kids or family that are into Legos. I guess think of primes as like the basic pieces of Legos. There's like a 2x2 kind of piece or a 1x4, but those are the basic pieces, but you can put them together, of course, connect them to build bigger things. But everything in Legos, no matter how complicated it is made up of the basic pieces. And that's kind of how primes are. They're the basic pieces of numbers, or the basic building blocks. Yeah. And every single integer can do that. But I guess for a prime, if a number itself is prime, let's say 7. If someone said to me, hey, can you find the prime factorization of 7? I would just say, 7 is prime. So it can't be broken down anymore. I mean, I guess technically the prime factorization of 7 is 7. Because it is a basic building block. It's like someone taking a Lego piece, just one Lego piece, and saying, hey, can you break this down into little pieces? And you say, no, this is one basic piece. If it was a bunch of pieces built together, yeah, I could break it down. But that doesn't really make sense, so it's kind of like that. And this is not too much of a complicated thing. It sounds like a complicated thing, but what we're highlighting here, the fundamental theorem of arithmetic states that each integer greater than 1 can be expressed as the product of prime numbers, and this prime factorization is unique. So that's just another way of saying there's only one way to write a number as the product of primes. So it's kind of like if the one we wrote earlier, 6 is 2 times 3. There's not another way to do that. I mean, as long as you've broken it down into its prime pieces. And I guess if I switch those around, 3 times 2, that we're thinking of that as the same thing. The order of the primes doesn't matter. But one thing I guess I should mention is prime factorization. When you do the prime factorization of a number, you don't want 1 in there. No 1. So it's, for example, 6. I would not say 6 is 1 times 6. That doesn't count. 1 doesn't count. It's kind of like the cheap divisor. 1 divides into everything, so it's not really interesting. I want to know what kind of prime numbers, 2, 3, and on, are the guys that divide in. So really, as we'll see coming up pretty soon, there's only one way to write the prime factorization of a number, aside from order of the primes. So that's the idea. It's kind of like the Lego idea. If I break something down, if someone's built something, I break the Legos down into each pieces. Those pieces are always going to be the same no matter how I broke it down. They might be in a different order, arranged in a different way on the table or on the floor, but they'll be the same building blocks no matter what. It's kind of basically it. But the first thing we're going to talk about in this section as far as examples go is we're going to see if a number is prime or not. If someone presents you with a number and they say, is this prime? How would you go about that, and how much work do you really have to do? We're going to try to, I know like in math, what we want to do is do as little work as possible. I guess in pretty much every avenue of life, that's the way I would like to do my life. But can I do less work? Is it possible to do less work? That's pretty much it. So what we want to do is tests for divisibility. I'd like to look at a number and already know right away, boom, it's divisible by 2, or no, it's not divisible by 2, or it's easy ways to know if it's divisible by something. So some of these you might already know, but they're kind of interesting. The first one for 2, a positive integer is divisible by 2 if the digit in the ones place is even. So basically, it doesn't matter how big the number is. If it ends in an even number, 0, 2, 4, then the whole thing's divisible by 2. So let's see, for example, if I'm going to make up a big old number, 127,840, and if whatever the last digit is, as long as I make it an even number, let's say 6, then that's divisible by 2. Divisible by 2. Check, yes, because it's 6. But if I rewrite that number, but let me change that last digit to 5 or something that's not even, not divisible by 2. So it's that simple. It's basically if you're an even number, you're divisible by 2. If you're an odd number, you're not divisible by 2. Easy peasy. That's all there is to it. So 2 is pretty simple. You can glance at a number really quick and know right away, boom, it is divisible or not divisible by 2. This one's more interesting, almost like even people that hate math and think it's silly or not fun, this actually gets them. They'll say, oh, this is kind of cool. A positive integer is divisible by 3 if the sum of its digits is divisible by 3. So let me explain what that means. But for example, the two numbers that they give here, they're saying, for example, 147 is divisible by 3, but 157 is not. So remember the word sum, that means add. So they're saying, if you have a number like the one they gave us first, 147, I'm going to take the digits of it, just the individual, ones in the hundreds place, 4 is in the tens place, 7's in the ones. I'm going to add them together in my head. Usually I'll just do that. Let's see, 1 plus 4 plus 7 is 12. Is that right? Yeah, I think so. And 12 is divisible by 3, right? Yeah, 3 goes into 12 4 times evenly. So that means 3 divides into the original number itself, 147, which is kind of interesting, I think. It kind of blows my mind. But the other one, for example, 157, if I take the digits of 157 and I add them together, 1 plus 5 plus 7 is 13. 3 does not divide into that. 3 does not divide. So the original number, 157, is not divisible by 3. Yeah, which is interesting. It seems, I'm actually not even sure why that works, but it works. I always tell myself I'm going to go figure that out or look it up, and then I don't. But one more. There are other divisibility tests, but I think this is probably good for our purposes. A positive integer is divisible by 5 if there is a 0 or a 5 in the ones place. So it's kind of similar to the 2 divisible by 2. If it ends in an even number, it's divisible by 2. If it ends in a 0 or a 5, it's divisible by 5. Otherwise, if it's anything else besides 0 or 5 in the ones place, we say, no, it's not divisible by 2. Or sorry, not divisible by 5. So we're going to test some numbers, but this is like, I guess the question is, down here in this example, it says, determine whether these numbers are prime. Okay, for example, if I look at the first guy here, 57, how many times do I have to divide it, or what do I have to divide it by to realize, you know what, I think it's prime? Like, how far do I need to go? Do I need to divide 57 by 2? I see if it's divisible by 2, 3, 4, 5, like everything until I get to 56? Or how? That's a lot of dividing. So what this note does here, it tells you kind of like the bare minimum you have to do to tell if it's prime. I don't really have to do all that work that I described. But it says, to determine whether a number n is prime, it's enough to test its divisibility by all prime numbers less than or equal to the square root of the number. So I'm going to actually write the square root of n, because they kind of specified here the number you're interested in general would be n. They're very clever. N for number. Wow. Math people are so creative. So for example, in this one, this number 57, I would kind of determine about 57. What's the square root of 57? It's kind of like 7 point something. I think 7.8 or 9. So all I have to do is test the divisibility of all the primes less than that. So I had to think to myself, what are all the primes? Oh, why is this not working? Primes less than that guy. So what are all the primes? And we only start primes at 2. We don't even talk about 1 being a prime. Whoops, where am I going? 2, 3, 4 is not prime. I don't need to test him. So I guess think of it this way. If I tested the number to see if it's divisible by 2, there's no reason really to see if it's divisible by 4, because if it was divisible by 4, it would also have been divisible by 2. So it's kind of like silly. Yeah. Anyway, so only the primes less than or equal to the square root of it. And let's see, 2, 3. The next prime after 3 is 5. And then I've got 7. After that, the next prime is bigger than my square root. So all I have to do is test to see if these guys divide into my number. So does 2, let's see, 2 divide into 57, question mark? Well, I could think back to that divisibility test. I'd say no, because the second digit is not even. 7 is not even. So far, if it was divisible by 2, I could say, nope, it's already not, 57 is not prime because I found something that divides in that's not 1 or the number itself. But I got a no on that one. I'm going to try the next guy. How about 3? Does 3 divide into 57, question mark? Let's see. How do we do that again? Oh yeah, we take the digits of the number. This one only has 2 digits. 5 plus 7, add them together. 5 and 7 is 12. Ooh, 3 does divide in. So this is a yes. Oops. Because 3 divides 12, the sum of the digits. So actually, that means this number is not prime. 57, not prime because 3 divides in. Not that they asked us to explain it, but yeah, that one's not prime. Okay. Actually, not that they've asked us, but in case it's in a textbook you read or a website or something, I forgot to kind of mention this, that the opposite of prime is composite. So if you see that word, you'll know what it means. I'm not going to test you on that number or that name, that word on a test or something, is not prime. It is composite. I guess the reasoning behind that is because it's composed of a bunch of primes. It's not just one building block. It's a bunch of blocks put together, so it's composed of other primes, I guess. Sort of, is maybe the reasoning. Okay, let's try 138. So the square root of 138, let's see, the square root of 138, I think is, let's see, I think it's between 12 and 13. It's somewhere, yeah, 12 is less than it, and 13 is bigger than it. So I want all the primes less than 13, basically. 2, 3, the same list, except I'm going to go a little farther, because the square root of this number that I'm interested in is a little bigger than the square root of the last number. 2, 3, 5, 7, 11 is the next prime after 7, and then 13, I guess I can test him. So the first few I'd like to test with the simple kind of ways that we've been looking at. 2, does 2 divide in? 138. Actually, right off the bat, that's a yes, because it ends in an even number. 8 is even. So right off the bat, I can already say 138 is not prime, it's composite. Not prime. Okay. Actually, that one was easier than I thought. And the more of these you do, the more you'll just kind of recognize right away, oh yeah, that's prime, that's not. If it's divisible by 2, it's pretty quick to check. How about 151? The square root of 151, I think if you were to put it in a calculator, it's between, let's see, I think it's actually between 12 and 13 also. Yeah, I think so. So I have to check all the same primes. Same list over here. Is it divisible by 2? No, because it doesn't end in an even number. That's a no. So I got to keep looking. I'm just looking for any prime that divides in this list here. This list, same list happens to be because these two numbers that I'm testing are pretty close together. Their square roots are between the same two whole numbers. Is it divisible by 3? Let's see. That means I need to add the digits together. 1 plus 5 plus 1 of the number itself. 5, 6, 7. So 7, but 3 does not divide 7, so no. Because 3 does not divide 7. That means 3 does not divide the original number either. Okay, so I've tried 2, I've tried 3. How about 5? 5, remember the divisibility test was, does it end in a 0 or a 5? That's it. So this one's no. This number that I'm interested in, 151, does not end in a 0 or a 5. I shouldn't say it, I should say 151. Does not end. Not that you have to explain it, but maybe later, if you're looking back at these notes and you say, wait, why was that a no again? All right, and then once we get past 5, we don't really have tests for these. Or I think there are tests, but they're kind of complicated, so I would just go ahead and try to divide them, either with a calculator or by hand. I'm going to try 7. Just 7. What's 151 divided by 7? Just literally take a calculator and try it. I think it's not a whole number. Let's see. I'm going to grab my calculator and try it. Just to be sure, but that's what you're looking for is, am I getting a whole number when I divide them or not? 151, nope, it's like 21.57 or something, so that's a no for 7. Gotta do that with 11 and 13, and then we're all done. Guess I should have given myself more room here. How about 11? Does 11 divide? I'm gonna try to divide on my calculator, or, by hand. What's 151 divided by 11? It's another decimal, so that's a no. So far, it's looking like it's prime. Something like that, so that's a no. Yeah, but if I got a whole number when I divide it, I would say yes. Last one. We said the last one on the list I have to test is 13. Is 151 divisible by 13? If it's a no, that means 151 must be prime. If it's a yes, then 151 is composite. Nope, it's another decimal. It's like 11.6 something. So I guess this guy is prime. Yes. Yes, prime. Because, the first two were composite, huh? Yep. Okay. How about 143, last one, and then we'll move on to the kind of the bigger, more interesting topic in this section that we're looking forward to. 143, okay. I think 143's got the same thing going on. The square root of 143 is in between the same whole numbers, because... Oh, no, actually, you know what? I think it's between 12 and 11. I'm sorry. You know what I'm doing in my head is, if you're interested, most people don't give a rip. But I'm thinking about what the square root of what is 12? Or in other words, what's 12 times 12? 144. And 11 times 11 is 121. 13 times 13 is 169. And that's how I knew. I was looking at the number, for example, 138 over here. I saw him and I said, well, he's between what two squares or what two whole numbers raised to a power? But now I've got one, it was close to the square root of 144. But yeah, the square root, this guy, 143 is between those, and the square root of 121 is 11, and the square root of 144 is 12. So really, I just need the primes that are less than 11, or less than or equal to 11. 2, 3, 5. Same list, but I'm stopping at 11. No need to test 13, because 13 would be too big. Barely too big, barely. Okay, let's try this guy. What do we say? What do we do again? Oh yeah, is 2 gonna work? No. This is where maybe I can work a little quicker. I'm kind of getting the hang of it. Does this guy end in an even number? No. So 2 can't work. How about 3? That's where I have to actually think about it. The digits of my number that I'm interested in are 1, 4, and 3. What's 1 plus 4 plus 3? 8. But 8, nah, 3 doesn't go into 8, so that's not going to work either. Okay. How about, does the number end in a 5 or a 0? Because I'm testing for divisibility by 5. No, it does not, so 5 won't work. How about 7? I would divide 143 by 7, and it's not a whole number. It's some kind of decimal, so 7's out. Okay, this is the only hope we have left. 11 times something is 143 divisible by 11. If it's a no, the number's prime. If it's a yes, it's a composite number. Let's see, I think it actually goes in 13 times. It's a whole number. That means it's not prime, it's composite. Because I found a number in my list, my tiny list that I have, that actually divides in evenly. Composite. Sorry, I wrote way too much on here. So that's the basic idea. Like I said, you could make it harder and do more work where you say, oh, let me divide the number by every number smaller than it. But really all that you need to do is divide it by all the primes, not all the primes that are smaller than the number itself, but all the primes that are smaller than the square root of the number itself. So it actually narrows the field down quite a bit, right? For 57, we only had to test 4 numbers. For the second number, we only had to test 6 numbers. For our third one, it was the same list, so 6 numbers again. And then the last number that we tried, it was only 5 numbers. So really, once you know that you don't have to do more work than that. It's not that bad. Okay, now we kind of talked about the definition of prime factorization, but now we're going to try to find the prime factorization of a bunch of integers. And then just to make sure that all our answers match, we're going to express duplicate primes as powers of that prime. So for example, if you found all the prime divisors and there were 3 of the same one, like here it looks like 3 5s, I wouldn't write them out like that, 5 times 5 times 5, I'd write that as 5 to the 3rd power. And then if the given number is prime, just write prime, because if a number is prime, it is its own prime factorization. And then what was the other thing I was going to say? Oh, I'd say the preference, I think we prefer to write primes a certain way. Write primes. If you have a bunch of primes in your prime factorization from smallest to largest, left to right. And I guess by that I mean, if we looked at that very first example, we looked at the very simple number 6. If someone said, well, what's the prime factorization of 6? I would say it's 2 times 3. I would not write, well, I shouldn't say not equal to, but I would say, if someone else said 3 times 2, I'd say, yeah, that's good, but we want to write it from smallest number on the left to biggest number on the right. So even though that one I just crossed out as correct, technically 6 is 3 times 2. We prefer it 2 times 3. I guess that way you can quickly check if we all got the same answer. So it's going to take a while, but I'm going to try to write the prime factorization of all these numbers here. It looks like quite a few, but you know, once you get the hang of it, it's not too bad. So I might as well start with the little numbers. Here we got 10. So I'll just say, start thinking about primes and dividing them in. Okay, primes. I'll just make a little list and maybe see if I need to make it longer for the bigger numbers, but I don't think I need to go too far. Prime numbers are 2, 3, 4 is not prime, 5 is prime, 6 is not prime, 7 is. And then 8 is not prime, 9 is not prime, 10 no, 11 is the next one. Maybe 13, that might be as far as we need to go. I might extend that list. So I'm going to look for any of these numbers to divide in. So I usually go one at a time. Let me see. So first I'm going to look at this number. Start with 10. Okay, which of those primes divide into 10? You can start with 2 or 5, but either of them work. 10 is 2 times 5 or 5 times 2. And then once I write it as something times something, I would check, are these both prime? If they're both prime, I can stop and I'm done. But if one of those or both are not prime, I have to do more work and break those down more. Are both prime. So we're done. But if one of those was not, like an example we'll see soon, then I would keep going. So there you go. 2 times 5 is the prime factorization of 10. That's it. So okay, we'll move on to the next one. How about 12? Let's try 12. And 12, you can break it down multiple ways because I think quite a few things divide into 12. But I'm really boring and, yeah, I don't really get creative. So I usually just start to have like a list of primes in my head and just start from the left 2. Does 2 divide into it? Well, it is even, so I'm gonna think, yeah, I think it is. 2 times what is 12, though? 2 times 6 is 12. Okay, now this is where I check. All right, am I done or can I keep going? Well, the first part of my prime factorization is prime, so I'm done with that. But 6 is not prime, so I actually have to break him down more. Now think about 6. What can 6 be? I'm going to kind of carry this 2 down. He's definitely going to be part of my answer for sure. But the 6, I don't want him. I want him. Yeah, it's kind of like someone built something, like a child built something with Legos, and there are 3 pieces, and you took one piece apart. If there were 3 pieces and you took one piece off, there are still 2 stuck together. So it's kind of like 6 is made up of 2 primes that I want to break apart now. I want to figure out what the very basic building blocks are. So what is 6? 6 is what times what? 2 times 3, I guess we did that earlier, right? And now I think all the numbers in my factorization here are prime, all prime. 2 is prime, the other 2 is prime, 3 is prime. So I think I'm done, but as it says, that's a perfectly fine answer, but we prefer to write any primes that are the same. Like here I have 2 2s. I prefer to write it as 2 to the second power. So I'll go, oh, that doesn't look good. Whatever, you know what I'm trying to say. 2 times 2 to the second power, and then there's only 1 3. You could write 3 to the first power, but there's no need. If it's just a 3, I know there's only 1 there. Yeah, so that's good. Looks good. And no matter how you broke it down, let me just maybe make a note on the side or something. 12 I wrote as 2 times 6, but notice some people might say, well, actually 12, you know, when I see 12, I think of 4 times 3 or 3 times 4. That would also work. So notice the way we did it, I wrote 2 times 6, but if I had done 4 times 3, I would right there assess, okay, which are either of those prime? Yes, 3 is prime, so he's good to stay, but 4 is not prime. I need to break him down. 4 is 2 times 2, and then there was a 3 already. But notice it ends in the same primes no matter what, right? I had 2 2s and a 3 in mine, and if you do it this way. So that what I'm trying to say, I guess, is that the process might look different as you go. If you break it down one way, like how I did 2 times 6, someone else might have done 3 times 4, and that's fine, but in the end, we'll get the same answer at the very end. As long as you write your primes from smallest to largest, left to right, and you write your powers as, or your like primes as powers, and then it should be the same answer no matter how you did it. Which is kind of, yeah, a lot like Legos, right? If a kid built something with Legos and said, can you take it apart for me? If they'd asked me or they asked you, we might take it apart a different way. But in the end, all the pieces would be there and they'd have all the same pieces no matter what. Okay, let's try 50. I'm just so boring. Every time I'm just thinking, does 2 divide in? That's my first thought. In this case, we got lucky again. 2 does divide in. 2 times 25 is 50. And now I assess, are either of those prime? Yes, 2 is prime, so he's good to stay, but 25 is not prime. So I need to do a little more work to break this down. I'm going to keep the 2, but 25 is going to be 5 times 5, right? Yeah, and remember, when you break it down and write it as something times something, you don't want either of those numbers to be 1. 1 is the most boring divisor. We're not a big fan of that. So I think I'm checking, let's see, do I have all primes? Yes, 2 is prime, 5 is prime, the other 5 is prime, of course. Now I just need to clean it up, maybe write it from smallest prime to biggest. It's kind of already in that order in my case, but if you had your 2 somewhere else, I'd move it to the left side. And then the 2 5s, wherever they are, if they're next to each other or not next to each other, write it as 5 to the second power. And no matter how you broke down 50, at the end you should have this, as long as you're following the rules and, you know, doing everything the way it's supposed to. Now I'm going to look at 49. Okay, 49, you probably already know what it is just by looking at it if you're familiar with numbers and dividing and stuff. But if I'm going to pretend like I don't know how to break it down, you know, just that way if there's a more complicated number later, I'll know what to do. I'm going to look at my list of primes over here. Okay, 2 is my first one. Does 2 divide into 49? No. 49 is not even. Does 3 divide in? Let me see. What's the sum of the digits? 4 plus 9 is 13. No, that's not going to work. Okay, not 3. 5? Does 5 divide into 49? No, because it doesn't end in a 0 or a 5. Okay, I guess on my list of primes, the first one that might go in is 7. And that's where I just divide it, you know, try to divide it with a calculator or in my head. 49 does divide by 7. It's 7 times 7, right? And then I would assess, okay, are either of those prime or both of those prime? In this case, they are. So I'm done, but I'm going to write it as 7 to the second power. There we go, and that's it. I know that one probably wasn't that bad. You could have done that one much quicker, but, you know, what are you going to do? Okay. And now I'm going to look at this next row here, 29. Okay, 29. Is it divisible by 2? No, because it doesn't end in an even number. Is it divisible by 3? Let's see, the sum of the digits, 2 plus 9 is 11. That's not going to work. So 3, no. 5, no, because it doesn't end in a 0 or a 5. Does 7 divide in? No. Okay, how about the next guy on the list? Does 11 divide in? I don't think it does. 13 doesn't divide in either, so I'm going to have to think about this. I'm suspecting this guy might be prime. I'm kind of writing that, but I'm going to kind of have a question mark. Is he? Then we might have to do what we did earlier and think about what's the square root of this guy. It's somewhere between 5 and 6. So all I have to do is look at the primes less than 5. So these were the only contenders, and we already checked. None of those divide in, so I was right. It is prime. Whew. All right. Sometimes I feel like I'm doing something wrong when I get prime as an answer. Like maybe there was a number that I missed or something, but no. How about 120? This next one. What of all my primes, I always start with 2. I'm so boring. 2 does divide in because it ends in a 0. 2 times 60, I believe. You can always check with a calculator or whatever. There you go. And either of those are prime. 2 is prime, but 60 is not. Let me break him down. I would just imagine now like this. You're starting a new problem and it starts with 60. Let's say you want to find the prime factorization of 60. 60, okay, what divides into 60? It's also even, so I'm going to break a 2 down out of it. 60 is 2 times 30. And now I assess, okay, am I ending with all primes? Well, so far, so good with the 2's, but the 30, that's a big number, and I think it has a lot of divisors, so he's going to need some work. I'm going to keep these 2 2's. Don't want to forget that they're there. But a 2 goes into 30 again, so really I can bring another 2 out of it. 2 times what is 30? It would be 15. Phew, so I'm getting a lot of 2's out of this thing. A lot of 2's divide into 120 there, huh? Wow. That's kind of misleading when I highlight that guy. There we go. All right. So I say, okay, how many of these guys are prime? Please tell me I'm done. 2 is prime, 2 is prime, 2 is prime. 15 is not prime, but I think we're getting close. I'm going to try to write, how many 2's did we have? There were 3 2's, but now 15 wants to be broken down. What can 15 be? 2 doesn't go into it, so I'm going to forget about that guy. But 3 goes into it. 3 goes into it 5 times. And then now I'm looking at all these guys. These are all prime, so that's good. But just to clean it up, I'm going to write all the like primes as a power. There are 3 2's, and then there's 1 3, so it's 2 to the 3rd power times that 3 times that 5. That's the one. Yeah, no matter, even though there are probably a lot of ways you could break that down, you should end in this exact same answer that we got, as long as you write things in the same order and all that. All right, how about 27? Does 2 go into 27? No. The next prime is 3. Yes, 3 does go into 27 9 times. Now I'm going to look at it. 3 is prime, but 9 is not prime. So I need to work on it a little more. Keep that 3, break 9 down. 9 is not divisible by 2, but it is divisible by 3. It's 3 times 3. And now I think we're finally ending in all primes. 3 times 3 times 3, or in other words, 3 to the 3rd power. Some of them are easier than others, and if it's easy, feel free to not really show much work. It's okay if it's something simple, you don't have to show work. How about 72? Okay, it's an even number, so I'm just going to go for 2. 2 goes into it, and you can always divide it, but I think it goes in 36 times. The 2 part is prime, so he's good to stay, but 36 needs to be broken down more into smaller primes. 36 is also even, so I'm going to write 2 times 18 is 36, right? Yes, okay. So I've got to keep the 2's that are there. Those are prime, but 18 is not prime. I'm going to keep going. It's even again. I'm breaking it down. It's kind of like a Lego, someone built Legos and I'm pulling the same piece off over and over. I'm like, how many green squares are there on this Lego set that someone built? Oh my gosh. Or whatever. But I pulled 2 2's off. Another 2 can come off. 18 is 2 times 9. It looks like we're all done with 2's, I think. We got 3 2's. Which is fine, but the 9 is not prime. He can be 3 times 3. Now we're fine. Now I scan. Is this actually all prime numbers? Yes. How many 2's are there? 3 of them. And how many 3's are there? 2 of them. That's kind of confusing. 2 3's and 3 2's. Say that 5 times fast. Okay, calm down. Why am I being weird? Yeah, so this is pretty much the process. And this is very useful actually in pre-calculus. There's something, or Algebra 2, if you take Algebra 2 in high school, you might have used this to factor polynomials, which is something you might see if you take more math classes after this. So this seems kind of like, okay, why would I ever want to do this? It's kind of like in English, did you learn how to diagram sentences? Like, this is the verb and this is the noun, and I'm like, why do I give a crap about this? Now this, I don't know about that. I can't answer the English thing, but there's a reason for this. This actually helps us do things in higher math classes. Anyway, so it's useful and it's kind of interesting, you know, kind of cool, I think. Anyway, what about this next guy? 175. All right, I'm going to look at my list. Does 2 divide in? No. Okay, it's not even at the end. Okay, what's the next prime? 3. Does 3 divide in? What's 1? Oh, 1 plus 7 plus 5. 13. Okay, no, 3 does not divide in. Okay, that's not going to work. The next prime is 5. Ooh, 5 does divide in because it ends in a 5. How many times, though? That's the question. 5 times what? Now, I'm too lazy to open my calculator. So I'm going to go 5. 37. Okay. Wait, is that right? That doesn't sound right. 5. Wait, what? Oh, what the heck? Oh, my gosh. 35. See what happens when I don't use a calculator? The calculator between my ears is not very smart. Anyway, there it is. So apparently 175 is 5 times 35. Okay. The 5 part's fine because he's prime, but I don't think 35 is because he ends in a 5, which means 5 goes in again. 5 times 7 is 35. I think I'm all done. There's 2 5s, which are prime, and a 7. So that's it. He's all done. Okay. Oh, God, 200. I'm freaking out about this guy. Really, 200? You know what? I just go by it. Okay. First prime is 2. Does 2 go in? Definitely it's even. 2 times 100 is 200. 2 is prime, but 100 is definitely not prime. 2 can go into it again. 2 times 50 is 100. I'm collecting 2s like crazy over here. I've got the same 2 2s. I got to break 50 down, though. He's not prime. Another 2 can come out. 2 times 25 is 50. I think that's all the 2s we got, though. I can, if I want to right now, even though I'm still working on the 25, I can start writing those 2s as 2 to the 3rd power. But 25 needs to be broken down. He's 5 times 5. So actually, that wasn't too bad. 2 to the 3rd power times 5 to the 2nd power. There were 2 5s in the end and 3 2s. Whew. Okay, last one. 143. That's a very random number. Does 2 divide in? So it's kind of like I want to factor it into primes, but this could be prime itself. I just got to test. It's not. Okay, 2 doesn't go into it because it's not even at the end. Does 3 go into it? Let me see about the sum of the digits. 1 plus 4 plus 3. What is that? 8? Nah, 3 doesn't go into it. 3 doesn't divide into 8, so 3 doesn't divide into this big number 143. What's the next prime? 5? No, because it doesn't end in a 0 or a 5. The next prime is 7. Let's see, does 7 go in evenly to 143? I don't think so. Nope. Okay, so 7's not going to work. What's the next prime? 11? Does 11 go into 1? Did we see this guy already? I feel like we saw this guy. Let's see. Oh, it does. 13 times. We already saw this guy. See, what happens sometimes when you have a bad memory, it's good. I'm getting extra practice. I think that's it, 11 times 13. And I'll check, okay, are both of those prime? If not, I have to break them down. No, they're both prime. Nothing divides into 11, nothing divides into 13. That's it. And that's pretty much the idea behind this section. Primes, they're interesting. Like I said, primes, you can use them in the math classes you take as you go, if you have to take more math classes. But primes are also interesting because I think it's complicated, but if they were, I think back in the wars, back in World War II, they used prime numbers and big, like the really large prime numbers to create codes that were not breakable or very hard to break. I don't really understand how it works, but it's interesting how prime numbers fit into computer science and yeah. Anyway, interesting if you're nerdy like me. Okay, thanks for listening.